We're back to chemistry. Podcast 6.3 is all about finding the volume of a mole of gas. So let's get right to it. The volume of 1 mole, of course, is going to change according to temperature and pressure. Think of a hot air balloon, right? If you heat it up, it's going to expand and get bigger and take up more space. So we're going to talk about the volume of a gas measured at what's called standard temperature and pressure. Standard temperature and pressure is what we call STP. So at STP, what would this mean? Standard temperature for gases is 0 degrees Celsius, the freezing point of water. So we always would measure the volume of the mole of gas at 0 degrees. And then standard pressure is 1 atmosphere. And in other words, at sea level, right? At sea level, you would have the entire Earth's atmosphere pressing down on you, and that would be 101.3 kilopascals. The kilopascal is the SI unit for pressure. And so 101.3 kPas, or 1 atmosphere, is considered standard pressure. So if we're going to be able to compare the volume for gases, then we have to keep it at the same temperature and the same pressure, or it won't be the same, right? So at STP, 1 mole of any gas always fills up exactly 22.4 liters. Okay, so I want you to visualize 22.4 liters. You know, a 2-liter soda bottle is going to occupy 2 liters, right? So picture that in your head. How much does a 2-liter soda take up? So use your hands, measure up the space about this big and this tall, right? Now, how many 2 liters are in 22 of these liters? 11, right? So 11 soda bottles. How much space would that take up? Find on your desk, like imagine stacking 11 soda bottles on your desk. How much space would that take up? A significant amount, right? And so it's not like some just little party balloon. It's bigger than that. It's more like a weather balloon. All right, so what that means for us, though, is that 1 mole that occupies 22.4 liters is then going to have how many particles? Remember Avogadro's number? 1 mole has 6.02 times 10 to the 23 particles. So every time there's 22.4 liters of a gas at standard temperature and pressure, it's going to contain 6.02 times 10 to the 23 particles. So we can use that amount in a t-table as a conversion factor. And you can flip it any way you need to so that it works in your t-table. Now let's talk about density. Remember, density is going to be equal to mass divided by volume, right? So if you know the molar mass, then all you need to know is the molar volume, which at STP is going to always be the same, 22.4 liters per mole. And so if you know the molar mass of any gas, you can determine its density at STP. And of course, you'll always know the molar mass because you can look it up on a periodic table, right? So the molar density will have the same t-table every single time we do it, except for the first square. The only thing that's going to change is this piece right here, the molar mass. Everything else looks exactly the same because we're always going to divide by this molar density, by the molar volume of 22.4 liters. So no matter what gas it is, we can get to its molar density. Let's do an example. Let's do the molar density of that gas ammonia. Remember, ammonia has the formula NH3. So if the molar mass of nitrogen is 14.01 and then hydrogen is 1.01, then that means the molar mass of ammonia is 17.04 grams per mole, right? So the molar density is going to be 17.04 grams per mole divided by 22.4 liters per mole. So let's get that calculator up. 17.04 divided by 22.4. And I get a molar density of 0.76, let's keep one more sig fig, 761 grams per liter. That's the density. There's the density of ammonia based on the molar mass at STP. So that's all there is to it, really. Find the molar mass and then divide by 22.4, and that's the molar density. Piece of cake. So here's the neat thing. This is what we call the mole roadmap. Because of moles, we can change particles to volume, or particles to mass, or volume to mass, or whatever we need to do. So see what you start with. Here's particles, right? So this could be atoms, or it could be molecules, or it could be what's called formula units. FUs, haha. Formula units if it's an ionic compound, right? But the way to get from anywhere to any place else, you've got to stay on the road. You have to go through moles first and then go where you're headed. You can't take any shortcuts. There's no off-roading here on the mole road map because you won't get where you need to be until you go to moles first. So we have a saying in chemistry. It is, when in doubt, what do? When in doubt, your best course of action is go to moles. When in doubt, go to moles. That's what we do. So let me show you how we do it. Here's a problem that involves a lot of different things from the mole road map, but now we know how to handle any of these things. How many grams are in 1.5 times 10 to the 25 molecules of CO2? So we're going to start with molecules, which is a type of particle. We're going to go to grams. Let's look at the road map. We're starting with particles. We're going to grams, but there's no off-roading allowed. We're going to have to go through moles first and then get there. All right, you ready for this? Okay, we're ready. We have 1.5 times 10 to the 25 molecules. I'm going to use molic for my abbreviation of CO2. And I want to change this to grams. So first I have to go to moles, right? So I'm going to put molecules on the bottom because crisscross cancels, and moles on the top. So in every 1 mole, how many molecules? Avogadro's number, remember? 6.02 times 10 to the 23 molecules are in 1 mole. And then from moles, we can now go to grams. For every 1 mole, how many grams are there in CO2? Well, let's add this up. Carbon is 12.01, and then there's 2 oxygens. So what's 32 plus 12? 44, right? 44 grams per mole? Well, 44.01. Okay, so now what do? In a T-table, we're going to multiply the top times the top, and then divide by what's on the bottom. So let's get our calculator out. 1.5, then the E button, 25, times 44.01. I didn't multiply by 1 with my calculator because I did not think that was necessary, And then we're going to divide by what's on the bottom, 6.02 E 23. Remember to use the E for your exponents. Do not use the times 10 with the little hat thing. That's going to give you the wrong algorithm, so you'll get the wrong answer. Okay, come back to our problem. Oh, gotta remember 1.1096.5. 2 sig figs. Okay, so I had 1096.5. Is that it? Yep. So that's quite a lot of grams, right? And I only get to keep 2 sig figs here. So I have to look after my second digit and see how to round this. That would be 1100 grams of CO2. Wow, that's a lot. That's like 1.1 kilograms of CO2. So then part A is solved. Part B asks us, what volume would the same CO2 occupy at STP? All right, well, let's clear some space. So let's solve part B. If I'm going to start with the same molecules of CO2, then I want to go to liters for volume, right? So how do I get there? Let's use this mole roadmap. So I'm at molecules. To go to moles, look at the map. What I want to do is have Avogadro's number on the bottom and moles on the top. Okay, so that's why I put it into my T table. And then in my next step, I'm going this direction now, right? So how do I go? Follow the arrow. This says liters is going to go on top and moles is going to go on the bottom. So let's do that. Let's set that up. I get 1 mole on top and Avogadro's number on the bottom. And then in my next step, I need 1 mole on the bottom and 22.4 liters on the top. Notice when I follow the arrows, it allows everything to cancel. Molecules cancels particles, and then moles cancels, and I'm left with liters. So now it's time for our calculator. 1.5 E25 multiply by the top, 22.4. Okay, hit enter before you start dividing by the bottom, 6.02 E23. If you don't hit enter, then you might get the wrong order of operations, so we'll just be careful with that. And I get 558 liters. Let's come back here. Okay, so 558 liters, but I only get to keep 2 sig figs, right? So look behind this number, and we'll have to round that up, right? So 560 liters of CO2. That's the volume of that same number. 1,100 grams of CO2 is 560 liters of CO2. That would take up a lot of space, right? Now the molar density is part C. So let's solve part C. What is the molar density of CO2? Remember our molar mass from the problem before was 44.01 grams per mole. And density is mass divided by volume. So I'm going to take the molar mass divided by the molar volume, 22.4 liters per mole. Moles is all gone now. And so 44 divided by 22 is half, right? Or 2? Yeah, 2. So let's see. 44.01 divided by 22.4. 1.96? Yep, pretty close to 2. Half, 2, whatever. How many sig figs? 3. 1.96 sounds good to me. 1.96 grams per liter. So now, here's my important question. If the density of water is 1, then shouldn't CO2 be less than 1? I want you to think about units, please. The density of water is 1 gram per milliliter. And so, if I have grams per liter, then how many grams per milliliter is that? Changing liters to milliliters is pretty simple. Times 10 to the minus 3 grams per milliliter, because milli is this 10 to the minus 3. So now compare. You can't compare when their units are different, but now that the units are the same, 1.96 times 10 to the minus 3 is certainly less than 1. And that makes sense, right? Because a gas should have a density less than the density of water so that gas would bubble up to the top, right, and float on top. This is what we do with our mole problems. When you're not sure which approach to take, get your roadmap out. You're going to get to use this in class. Follow the arrows from your starting place to your target, and you'll get it right every single time. This shows you exactly how to put it in your T-table so that you can get it right. Okay, it's going to take some practice, and you're going to need to do the practice yourself. So make sure that you're not just writing down what answer your friends are getting. You work it through yourself so that you know how to solve every problem. See you guys soon.